Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will learn how to apply concepts from integrated rate laws when given a specific set of kinetic data. To get us started, we're going to go ahead and look at this first problem. Here we have reactant A decomposing to produce product B and product C. So based on the given kinetic data that's provided for us, we're going to go ahead and determine the order of reaction for reactant A. And so we've been able to determine orders of reaction once before through the method of initial rates. Now, typically, the kinetic data that's going to be given to us for method of initial rates contains multiple experiments with differing initial concentrations of the reactants, as well as the initial rate of the reaction per each trial or per each experiment. I want you guys to notice that this kinetic data only provides information on the concentration of reactant A against time. And so to determine the order of reaction, what we're going to do is we are going to manipulate this data and later plot it on a graph. In other words, we're going to create a series of tests to determine if this chemical reaction follows first order, second order, or zero order kinetics. And so for us to understand what we're about to do, I'm going to go ahead and go back to 3 slides that was covered in the previous lecture video. And so if you wanted to determine if the chemical reaction is undergoing zero order kinetics, then what you're going to do is you guys are going to plot the concentration of that reactant against time. So in other words, there is no manipulation of the concentration values. It's just the concentration of the reactant against time. And so if the result produces a line, a straight line going down, in other words, it has a negative slope, then that would be a positive confirmation that the reaction is undergoing zero order kinetics. Now, if the points on the line do not match up, in other words, for example, it curves this way or it slightly curves that way or whatever. So basically, if it is not a straight line going down, if it does not have a negative slope, then that would tell the reader that the chemical reaction is not undergoing zero order kinetics when you plot the concentration of the reactant against time. Now, if you wanted to determine if the chemical reaction is undergoing second order kinetics, what you guys are going to do is you're going to manipulate the concentration of the reactant such that you're taking its reciprocal. In other words, 1 divided by the concentration of the reactant. And that's going to, so the result of the reciprocal of the concentration of the reactant is going to be plotted on the y-axis. And so you're going to go ahead and plot the reciprocal of the concentration against time. And if the graph that's produced is a straight line that's going up, in other words, it has a positive slope, then that would be a positive confirmation that the reaction is undergoing second order kinetics. And so if the line, if the graph slightly tilts one way or the other, in other words, if it is not a straight line going up, in other words, it has a positive slope, then that would inform the reader that the chemical reaction is not undergoing second order kinetics. So it must be a straight line with a positive slope. Last but not least, if one wanted to determine if the chemical reaction is undergoing first order kinetics, then you guys are going to manipulate the kinetic data such that instead of plotting concentration on the y-axis, you're plotting the natural log of the concentration on the y-axis, and you're plotting that against time. And so if the result of that graph produces a straight line going down, in other words, this line has a negative slope, then that would be a positive confirmation that the reaction is undergoing first order kinetics. And so if the line slightly tilts one way or another, in other words, if it is not a straight line going down, then that would inform the reader that the reaction is not undergoing first order kinetics. All right, and so what we're going to do is we're going to apply this concept to this problem to determine the order of reaction with respect to reactant A. So looking at the axis for this specific data, notice that it's concentration against time. And whenever you guys are plotting concentration against time on a graph, what you're really doing is you're testing for zero order. And so before I plot this on a graph, I'm going to go ahead and manipulate this kinetic data so that way I can test for first order, and I can also create a table that tests for second order. And so I'm going to go ahead and create a table that tests for first order. And that table will have a y-axis such that the resulting value is from the natural log of the concentration of the reactant. Okay. So the y-axis is going to reflect the natural log of the concentration of reactant A against the same time period. Okay. So I do want you guys to notice that for all three plots, the time is not going to change. And so it's just 10, 20, 30, 40, 50, 60 minutes. And so to create my new data points for my y-axis to test for first order, what I'm going to do is I'm going to take this number and I'm going to take the natural log of it. So if you take the natural log of 8.23 times 10 to the negative 3, if you punch that in your calculator, what you're going to get is negative 4.800. And so just to review the rules of sig figs for natural logs and for logs, if there are 3 sig figs, then you need to record 3 places after the decimal. And so once again, I'm going to apply that same pattern for the second point. So if I take the natural log of 6.74 times 10 to the negative 3 and put that in my calculator, I'm going to go ahead and get a value that it's negative 5.00. Okay. And so I'm going to go ahead and apply that same logic for all of these points that remains. And so when the time is 30 minutes, if I were to take the natural log of 5.52 times 10 to the negative 3, that's going to give me negative 5.199. And if I were to take the natural log of 4.52 times 10 to the negative 3, I'm going to get negative 5.399. And if I were to take the natural log of 3.70 times 10 to the negative 3, that's going to give me negative 5.599. And last but not least, the natural log of 3.03 times 10 to the negative 3 is going to give me negative 5.799. Okay. And so this is going to be the values that I'm going to plot to test for first order against the same time period. And so for second order, if I want to test for second order, remember that the y-axis is going to reflect the reciprocal of the concentration of reactant A in this scenario. In another scenario, it just might be reactant B or an actual reactant such as like nitrogen dioxide or something. And so when you guys are plugging in, or whenever you guys are manipulating the raw kinetic data into, and you're trying to fit it for second order, what you're really doing is you're taking 1 and you're dividing it by this value over here. So in this case, it's going to be 1 divided by 8.23 times 10 to the negative 3. And if you plug that into your calculator, the value that you're going to get is going to be 122. And so if you apply that same logic to the second point, so I'm going to take 1 and I'm going to divide it by 6.74 times 10 to the negative 3, the value that I'll get is going to be 148. And so I'm going to go ahead and repeat that same procedure for the last 4 points. And so the resulting values, if I take the reciprocal of those concentrations, is going to be 181, 221, 270, and 330. So now that I have all of my data points filled in, I can go ahead and plot all of these data points on 3 separate graphs. And each of those graphs is going to test for a specific order of reaction. And so I'm going to go ahead and test for 0 order. And so I'm going to go ahead and graph these points, and I've kind of already done so. Okay. So I'm going to go ahead and zoom in here. And so I'm going to go ahead and erase this pink line for now. And so basically, I've plotted all of these points onto a graph. And I want you guys to pay attention to the axis. So notice that it is the concentration of reactant A against time. And so what we're doing is we're testing for 0 order. And I'm putting a question mark to reflect whether or not it is 0 order or not. Anyways, and so if you plot those points, it kind of looks like it's a straight line, right? But to really confirm whether or not it's a straight line or it curves, what you want to do is you want to connect the first and the last point. And so notice that once I've connected the first and the last point, there's a whole bunch of points that does not fall on this purple line. And so since not all of the points line up on that purple line, then that means that the points kind of curve. And when the points curve, it's telling us as the reader that this reaction fails the second order test. In other words, this chemical reaction is not undergoing 0 order. So here we're going to write a fail for the 0 order test. All right, and so I'm going to go ahead and plot second order. So all of these points, I'm going to zoom in real quick, or zoom out. Okay. So I'm going to go ahead and zoom out real quick. So all of these points here is going to already be plotted on a graph. So I've kind of done that ahead of time. And so this is the result of that graph. And so looking at the axis, if I take the reciprocal of the concentration and plot it against time, what I'm doing is I'm testing for second order. And once all the points has been plotted from the table, I'm going to go ahead and see if all of these points fall on a straight line. And so I'm going to go ahead and connect the first point to the last point. And I want you guys to notice that there are points on this graph that do not fall on that purple line. And so this is telling us that this graph slightly curves. And so if the graph slightly curves, then that means that it fails that specific test. So in other words, this chemical reaction is not undergoing second order. So it fails the second order test. And so if it's not zero order and if it's not second order, then it must be first order. And so we're going to go ahead and still plot this on a graph. And basically the graph looks like this. So zooming in on this graph, we're going to go ahead and plot the natural log of the concentration of A against time. So this axis, natural log of concentration of A against time, is trying to test for first order. And so if I didn't have this line over here, if I wanted to test whether or not, or determine whether or not all of these points fall in the straight line, I'm going to go ahead and take the first point and connect it to the last point. And as you can see, before and after I erased that pink line, all of the points fall on that line. So this lets the reader know that this chemical reaction is undergoing first order kinetics. So in other words, since all the points fall on that line, it passes the first order test. And so this chemical reaction is undergoing first order kinetics. And so all of the characteristics, all of the equations that we discussed in the previous lecture video now applies to this specific chemical reaction, simply because it passes the first order test. All right, so what we're going to do next is we're going to do some follow-up questions. But before I do so, I just want to quickly review, because it's such an important concept. To create these tests for zero order, first order, second order, we're going to take this raw data and we're going to take the natural log of it to test for first order. We're going to take the reciprocal of it to test for second order. And so once we have all of the data filled out, we're going to plot them on 3 separate graphs. And what we're looking at is, or what we're looking for, is a straight line. And so if, in this scenario, since the straight line is observed with a negative slope, is observed for when the natural log of concentration of A is plotted against time, that means it passes first order. All right, so what we're going to do is we're going to do some follow-up questions. So now that we know that this reaction is undergoing first order kinetics, we're going to calculate the rate constant K for this specific reaction. And after we determine the value for K, we're going to write the complete rate law for this chemical reaction. So now that we know that this reaction is undergoing first order kinetics, all of the equations that's related to first order kinetics now applies. And one of those equations is going to be the natural log of the concentration of reactant A at any given time period equals to the negative K times this by time plus the natural log of the concentration of A at the initial time period, or the initial concentration. And so this equation is the expanded form of the integrated rate law for first order kinetics. And if you guys recall, we can go ahead and overlap this equation through the equation of the line, y equals mx plus b. And so by expanding the integrated rate law into its straight line plot form, we can calculate the rate constant k by determining the slope of the line. And so here we have negative k is equal to m. Since we're solving for k, we don't want a negative in front of it. And so we're going to go ahead and transfer that negative to the other side. So we're going to divide by -1, such that the rate constant k is equal to negative m. And so remember, m is a slope. And so we can go ahead and expand m to an equation such that the rate constant k is equal to negative parentheses y2 minus y1 over x2 minus x1. And so all I really need is 2 points on that graph, and it can be any 2 points. And if we plug this into the slope formula, we should be able to calculate or determine the rate constant k. And so looking at this graph, you guys can choose any 2 points. So the 2 points that I'm going to choose is simply going to be the first and the last. Okay, so I'm kind of describing that whole line, the slope of the whole line. But you guys should be able to get the same answer if those 2 points was compared between the first and the second, for instance. And so looking at the value of this point, we have an x value of 10 and a y value of negative 4.800. Actually, it's going to be 10.0 if I wanted to record the sig figs that's reflected in this table. So basically, I'm comparing the first point and the second point. So this is going to be, I'm just going to go ahead and label this as x1, and this is y1, and this is y2, and this is x2. I guess this would be a much simpler way to determine the points that I'm going to use to calculate the slope of the line. Okay. So just for completion, I'll go ahead and write this point in. So this is going to be 60.0. That's describing the x-axis, and the y-axis is going to be negative 5.800. Okay. So the numbers are rounded when it's being graphed. All right, so looking at our y2 value, the value for y2 is going to be negative 5.799 or 5.800 minus the y1, which was negative 4.80. And we're going to go ahead and divide this by 60.0 minus 10.0. So that's reflective of x2 and x1. And so if I were to follow through with my math, I'll get negative parentheses, negative 0.999 over 50.0. And so if I were to put this into my calculator, I get a raw value of 1.998 times 10 to the negative 2. And if I were to round to the correct number of sig figs, I'll get 2.00 times 10 to the negative 2. Now remember, the rate constant k has a very specific unit. And since we're undergoing first order kinetics, the unit for k for first order kinetics is going to be 1 per time. And so in the previous lecture video is 1 per second. But if you guys recall, the unit for time in this example is minutes. And so the unit is going to be 1 per minute. Okay. And so now that we know the value for k, we're going to go ahead and write the complete rate law. So remember that this is undergoing first order kinetics. So therefore, the rate of the reaction is equal to k times this by the concentration of A raised to the first power. And so now that we've figured out what k is, we're going to go ahead and erase that. Let me move this over to the side. Let me just rewrite it then. So the rate is equal to 2.00 times 10 to the negative 2, 1 per minute, times this by the concentration of A raised to the first power. Okay. So this would be the complete rate law for this chemical reaction. All right. And so once we know that the order of reaction is first order, we can go ahead and apply all of these equations and answer these questions. And so for part B, we're going to calculate the half-life for this reaction. So remember that there are 3 different half-life equations. And the half-life equation that we're going to use should reflect first order kinetics. And so that equation is going to be T1 half, where the half-life is equal to the natural log of 2 over the rate constant k. And so the rate constant k is what we just solved for in part A. And so to calculate the half-life for this reaction, all we're going to do is replace the rate constant k with the value that we obtained in part A, which is going to be 2.00 times 10 to the negative 2, 1 per minute. And so if we plug that into the calculator, it turns out that the half-life for this reaction is going to be 34.7 minutes. Okay. So notice that if you have a denominator in the denominator, it then becomes, it goes to the top, it's a numerator. And so you guys can prove this by doing keep, change, flip. And so basically divide fractions. All right, so now that we've determined that the half-life of this reaction is 34.7 minutes, this tells us that since this is first order kinetics, all consecutive half-lives for first order kinetics will have the same half-life. Okay, so the first half-life is going to be 34.7 minutes. The second half-life is going to have the same time interval, 34.7 minutes. Third half-life is going to be the same, and so forth and so forth. So that's characteristic of first order kinetics. All right, so what we're going to do next is we're going to calculate the initial concentration of reactant A. And so if you guys were to look at the kinetic data, so I'll just start here, or actually I'll go ahead and look at this one. So notice how the time period starts at 10 minutes. So this is technically not initial concentration since time has already elapsed. The initial concentration is at time 0. And so what we're going to do is we're going to use the data that's provided to calculate the initial concentration of reactant A. And so to do this, we're going to rely on the expanded form of the integrated rate law for first order kinetics, such that the natural log of the concentration of A at any given time period is equal to negative K times T plus the natural log of the concentration of A at time 0. And so what we're solving for is this term. And so since we're solving for this term, that means we're going to move some terms around. And so since the relationship here is going to be, negative and positive, we're going to go ahead and add KT on both sides of the equation so that this term can be canceled out. And so we're going to basically move this to the other side. And so the natural log of the concentration of A at any given time period is plus K times T is equal to the natural log of the initial concentration. Okay. And so for us to solve for this term, we need to plug in some values. And so K is given to us from part A, which is 2.00 times 10 to the negative 2, 1 per minute. Now, notice that this concentration of A is at any time period. And so what we're going to do is we are going to choose any of these points and take the natural log of it. And so, for example, if we chose the first point, then the concentration that we're going to be using is going to be 8.23 times 10 to the negative 3, and the time is going to be 10 minutes. Now, if we chose the second point, it's going to be 6.74 times 10 to the negative 3. However, the time is not 10 minutes, it's going to be 20 minutes. So just make sure that you guys are consistent with the points that you guys are using. And so I'll just go ahead and use the first one. And so I'm going to go ahead and take the natural log of 8.23 times 10 to the negative 3. And remember, this value, this result, was recorded at a time period of 10 minutes. So therefore, T in this example is going to be 10 minutes. And so if I were to put all of these pieces together, I have the natural log of 8.23 times 10 to the negative 3, and we actually already calculated that. So this whole thing is simply going to be negative 4.800 plus 2.00 times 10 to the negative 2, 1 per minute, times this by 10 minutes. That's going to equal to the natural log of the concentration of A at time 0, so initial concentration. Okay. And so if you guys put this into your calculator, well, first and foremost, notice that the units for minutes will cancel. And let's see here. We know that this value here is going to have concentration units. Okay, so remember that 8.23 times 10 to the negative 3 is the concentration at 10 minutes. Okay, and so basically, if you guys put this into your calculator, what you guys will obtain is negative 4.600, and that is going to equal to the natural log of the initial concentration, which is what we're looking for. And so to solve for this term, we're going to perform the opposite operation of the natural log. And so we're going to take the anti-natural log. We're going to e both sides of this equation. And so in your calculator, you're going to press second natural log, or second ln, and your e should pop up. Then you're just going to go ahead and type in negative 4.600. And so when you plug that into your calculator, the concentration, the initial concentration that you guys are going to get is going to be 1.01 times 10 to the negative 2. And so notice that if you take the opposite of a natural log in terms of sig figs, since we have 3 decimal places, that means we have 3 sig figs in our final answer. And so since we're talking about concentration units, since there's the bracket that's present, we know that the unit is going to be molarity. Okay, and so here we have now just found the initial concentration of this reaction. And so one way to check if this number makes logical sense is if you compare that with the table. So notice that this first point at 10 minutes is going to be 8.23 times 10 to the negative 3. And so at time 0, that number should be larger than this point. And it is, because it's 1.01. Oops, let me just write it down here. So it's 1.01 times 10 to the negative 2. And times 10 to the negative 2 is much larger than times 10 to the negative 3. Okay, so that answer makes logical sense. So the last thing that we're going to look at is the concentration after 95 minutes has passed. And so once again, we're going to utilize the expanded form of first order kinetics, of the integrated rate law for first order kinetics, which is the natural log of the concentration of A at any time period, which equals to negative K times T plus the natural log of the initial concentration. And so now that we know the initial concentration of this reaction, we can now solve for the concentration of reactant A at any time period. And so since the time period is 95 minutes, I'm going to go ahead and put a note that this is reflective of 95 minutes. Oops. Okay. And so this is what I'm essentially, this is essentially what I'm looking for. And so I'm just going to go ahead and plug in my values. So I know my rate constant K from part A. So that was 2.00 times 10 to the negative 2, 1 per minute. And then I'm going to multiply this by 95 minutes because I want to know how much remains at that time period, or after that period of time has passed. And times that by the plus the natural log of the initial concentration. And the initial concentration is just what we just solved for, which is 1.01 times 10 to the negative 2. Okay. So the units of minutes cancels, leaving us with just the units of molarity. And so if I were to plug in all of these terms in the calculator, let's see here, I am going to get negative 1.90 molar. And that's going to equal to the natural log of the concentration of A after 95 minutes has passed. And so to solve for this term, I'm going to perform the opposite function of the natural log, which is the anti-natural log. So I'm going to e both sides of the equation. And so in your calculator, you're going to press second ln and then type in negative 1.90. And so since, let me just write this down. So the final answer is going to be approximately 1.51 molar. Now, since I'm taking the e, which is the opposite of natural log, since I have two sig figs, that means I'm going to record two places, or since I have two places after the decimal, sorry, that means I'm going to record two sig figs. And so here, my final answer is going to be 1.5 molar. So after 95 minutes has passed, the concentration of reactant A is going to be 1.5 molar. Let me see if I'm missing something here. So let me just check my math real quick, because this does not make sense. So I have 2.0 times 10 to the negative 2 times this by 95, times that by negative 1. Okay, so I'm going to add that by the natural log of 1.01 times 10 to the negative 2. And let's see, okay, I guess I made a mistake here. So, sorry, I didn't add the natural log into this value. And so I'm going to erase this part right here. And so what I get is going to be negative 6.495, and the list goes on. So that's going to equal to the natural log of the concentration of A sub T. Okay. So I'm going to go ahead and E both sides. And, okay, I'm getting a better answer. So the concentration of A after 95 minutes has passed is going to be 1.51 times 10 to the negative 3. And so, let's see here. For sig figs, I'm just going to go ahead and round this to 1.5 times 10 to the negative 3 molar. All right. So hopefully you guys have followed my train of thought, my logic, and this will demonstrate, hopefully this demonstrates how you can apply some concepts of integrated rate laws into a problem type setting. Okay. So here we worked through graphs, and after we determined the orders of reaction, we applied that to some questions that was asked. All right, so the next lecture video is going to showcase the use of integrated rate laws through word problems. In other words, you guys are not going to be given this type of kinetic data to work from. You guys are going to be given very specific scenarios. And so I'll see you guys in the next lecture video.